gentlemen, to our last unit before February break. It's going to be a short one. We have 3 days and then a quest. It's only 6 questions. Good news is you do get a formula sheet for this quest. So all the formulas for arithmetic and geometric sequences in series you will receive a formula sheet for. So that's the good news for this unit. We're going to start off day 1 with Pascal's triangle. So some of you may remember this from last year. Pascal's triangle is used for a binomial expansion. If you had something like 2x plus 7 raised to the 5th power, you don't want to write that out 5 times and then multiply it all out. So what we're going to do is we're going to fill in Pascal's triangle here. So Pascal's triangle starts with 1. This is considered row 0. And then we have row 1. So every row always starts and ends with 1. So as you go down through, every row is always going to start and end with 1. Now, in order to get these empty ones in this honeycomb figure here, you're going to add the 2 numbers above it. So this would be a 2, and then these 2 would be 3s. And then the next row would be 1, 4, and then this one would be 6 because you're adding the 3 and 3 together. 4, 1, and let's just go down to row 5. 5, 10, 10, 5, and 1. So these help to give you an initial coefficient when you are expanding a binomial. So let's take a look at the first one. It says here x plus 1 to the 3rd. So whatever the power is, that's telling you what row to use. So this one would be use row 3. So those coefficients are 1, 3, 3, 1. I always spread mine out to give me room to do my other terms associated with this. So I'm looking at the first term of the binomial, it's an x. The first term always starts to whatever the exponent is and then subtract by 1 every time. So x to the first. Now this is going to be x to the 0, which is going to turn out to be 1, so there's really no point in writing that. Next thing I'm going to do is I'm going to take the second term in the binomial. That always starts out being raised to the 0, and that increases by 1 every time. So this would be 1 to the 0. Now think about this for a second. You're going to have 1 to the first, 1 to the second, 1 to the third. It's not going to matter. Everything's just going to be 1. Since this binomial is a sum, everything is going to be positive. So this is going to give you x to the 3rd plus 3x squared plus 3x plus 1. And then that would be what you would get had you taken that binomial and multiplied it out 3 times. Now as we take a look at the subtraction of your binomial, the only thing that's going to change here is you're going to alternate signs in your expression. So this is going to be a positive x to the 3rd, a negative 3x squared, a positive 3x, and a negative 1. So all that negative does is just has you alternate the signs of your expansion. All right, so what I want you to do is I want you to try this next one on your own. So go ahead and pause the video, and then when you're ready, go ahead and hit play again, and the answer will be there for you. Okay, how'd you do? Should have ended up with 16x to the 4th minus 96x cubed plus 216x squared minus 216x plus 81. Okay, if you didn't get that, go ahead and pause the video, take a look at how I set up each term. Don't forget to alternate your signs. All right, let's go ahead and jump into sequences and series here. We have some important information. These are just the different terms and variables that you deal with throughout sequences and series. So a sub 1 represents the first term in the series or the sequence. Okay, so that's going to give you your first term. A sub n is any term. So if I wanted, for example, the 10th term, it would say a sub 10. N is just a number. It's going to help you determine what term you're looking to find or what term you're working to work with. R is your common ratio. This is used in geometric sequences. Your D is your common difference that is used in arithmetic sequences. Okay, now these two S's here, they're going to represent the sums of a sequence, which is called a series. So when it's just an S with no subscript there, that's the sum of an infinite series. And then if it's got the subscript n there, that's going to be the sum of a finite series. So one that doesn't end versus one that does end. All right, so the first thing we're going to do, I'm going to go over how to find the first term, and then you're going to go through and find the other terms in each one of the sequences here. So I'm going to do the first term for each one, and then I want you to go back through and find terms 2, 3, and 4. So in order to find the first term, I'm giving n a value of 1. So that 1 gets substituted into the expression. So that gives you 3 times 1 minus 2. So that's going to give you 3 minus 2, which is just going to give you 1. All right, so then you guys can do the rest of that one. And if I want to find the first term in this sequence, I'm going to do 3 plus negative 1 raised to the first. So this is really 3 minus 1, and that's going to give you 2. So what I want you to do now is I want you to find the second, third, and fourth terms of each sequence, each time changing your n value. And you can go ahead, pause the video, and hit play when you're ready to join me. So as you can see here, excuse me, changing that n value, finding the different terms of each sequence. In part A, you had 1, 4, 7, and 10 was the pattern that you were establishing here. And then in part B, it was alternating back and forth from 2 to 4. Okay. All right. So now that's if I give you the formula for the sequence and then you give me the terms. In the next part here, we're going to look at the terms and then we're going to come up with a formula, so to say, for each sequence. In working with sequences, you want to look for a pattern that's occurring in your terms. So for the first example, we have 1, 3, 5, 7. So you should notice that the pattern that's happening is everything is being, 2 is being added to every number in order to get to the next term in the sequence. So when we want to write a pattern for this, we're going to call it a sub n so that I'm going to write a formula so that I can find any term. And this is going to end up being 2n minus 1. So what happens is I have an n value such as 1. I substitute 1 in for n. I get 2 times 1 minus 1. That gives me 1. Okay, then I move to 2. So when I put 2 in here, this gives me 2 times 2 minus 1, which is going to give me 3. So the fact that this had a common difference of 2, you add 2 every time, that's going to come into play here pretty soon. Now, when you take a look at the next one here, this one's a little bit trickier. And so what I want you to do right now is I want you to just take a look and see if you can notice any kind of pattern that's happening here. 2, negative 5, 10, negative 17. So just pause the video and think about that for a minute and see if you can come up with some kind of pattern. All right, so let's see what you came up with here. The way that I went about thinking about this is I said, all right, first of all, I need to take care of the fact that this is alternating positive, negative, positive, negative. So what I did was I said, well, if I take negative 1 and I raise it to the n plus 1, that will make every even term in the sequence a negative number. Okay, so if I put, that will take care of that'll take care of all of the positive and negative happening. So for example, when I put 1 in here to find the first term, 1 plus 1 is 2, that's going to end up squaring that, which is going to make that positive, which is going to give me my first term positive. So by doing this, I'm going to have every even term in my sequence, the second, the fourth, the sixth, they're all going to end up being odd. Now the next thing I had to do was realize the pattern that was happening. So I happened to notice that 2, 5, 10, 17, they were all 1 more than the square of a number. So after this, I took the expression n squared plus 1. So 1 squared plus 1 is 2. 2 squared is 4 plus 1 is 5. So that took care of the pattern 2, 5, 10, negative 17. Okay, so this is kind of the pattern that I would follow in order to continue to get more terms in the sequence. So now we have a general form for each one of those sequences. So now what I want you to do is I want you to find the 100th term. So that would be a sub 100 for each one of those. So I've given you the rule. You're going to put 100 in for n and find me the 100th term of both sequences. Okay, how'd you do on those? It's pretty basic, substituting in a value, simplifying your expression. I'm sure at some point in your extensive math careers, you guys have heard about recursive sequences. So recursive depends on previous terms in order to establish the next term. So there's no common difference, there's no common ratio between each term. There's just a pattern that occurs. So one of the famous recursive sequences is the Fibonacci sequence. So if you know the Fibonacci sequence, you understand how you get from one term to the next. There's a couple little comics down there, a little math humor for you to take a look at. But what we're going to do is we're going to establish the first 10 terms of the Fibonacci sequence. So I'm going to tell you what let's see, the first term is 1, the second term is 1, the third term is 2, and the fourth term is 3. So see if you can figure out what the pattern is for the rest of the Fibonacci sequence. Okay, did you figure it out? So in the Fibonacci sequence, for those of you that don't know the Fibonacci sequence, the Fibonacci sequence is based on the previous two terms. So for example, you would take 1 plus 1, and that's how you get 2. But then in order to get 3, you would have to take, oh, that was a really bad curly bracket. Okay, you would have to take 1 plus 2, and then that's how you get 3. So then you do 2 plus 3, that's how you get 5. 3 plus 5, that's how you get 8. So that's one of the most famous Fibonacci sequences. So in just general terms, using variables, you can take a look up above on how the Fibonacci sequence is defined. So in this next example, it gives you the rule for the recursive sequence. It wants you to list the first 5 terms of the sequence. So it gave you the first term as 6. So when you have expressions such as n and then n minus 1, if I'm going to put in, let's say for example, 72 for n, then n minus 1 would just be 71. So that it's just the term before the previous one. So recursive makes it really difficult to find numbers that are further out in your sequence because you always have to know the one before it. So what I want you to do is use the formula right now. Use the recursive formula. Start with the first term. Find the second, third, fourth, and fifth of each one of these recursive sequences, or this one recursive sequence. So if you'll notice, I'm just taking the term that I found before. So 6 went in here, and then 17. I come and use here, and then 39, I come and use there, and then 83 got used in there, and then my last term being 171 for the first 5 terms of that sequence. So you're just using the term before it in order to find the next one. Okay, now we're going to actually write the formula. So working a little bit backwards here, I'm giving you the terms of the sequence, which is 2, 4, 14, and 41, and you're going to try and figure out how to get from one term to the next. So take a look there and see if you can find any patterns occurring. All right, what did you come up with? Okay, some pretty good ideas here. So one of the things that I looked at was I looked at the difference between each one of these. Now there's not a common difference. Like the difference between these is 3, and then the difference between these is 9, and then the difference between those is 27. So if you notice though, to get from 3 to 9 to 27, everything gets multiplied by 3. So I looked at that and said, I wonder if that has something to do with the pattern of the recursion formula. So I said, all right, if I'm going to take a term, so I started with n plus 1, I said if I take the term before it, which would be a sub n, okay, and I take into consideration, I said, all right, what if I take and I do 3 times the term before it? So if I take 2 and I multiply it by 3, I get 6. And then if I take 5 and I multiply by 3, I get 15. And if I do 14 times 5, I get 40. So what's happening is I'm always 42, sorry, multiplied that wrong. And then I have to subtract 1. So every term before it, if I multiply it by 3 and then subtract by 1, I come up with the next term. So that was the pattern for that one. So sometimes looking at the common difference can help kind of figure out what the pattern is. Quick review of factorials. Sometimes they like to stick factorials into your sequences. Again, this is just a matter of substituting in your value for n. So you have an n factorial, and then you have a 2 to the n in the top. So quick review before I have you find the first 5 terms. If I wanted to do 4 factorial, that's just 4 times 3 times 2 times 1. Now on your scientific calculators, I couldn't tell you where the factorial button is, but if you come into class and show me that you found it, I'll give you a big pat on the back. So now go ahead and find me the first 5 terms of this sequence. Okay, hopefully everybody came up with 2, and then another 2, and then 4/3, then 2/3, then 4/15. Okay, so everybody should have gotten that right. All right, let's do a quick review of summations using the sigma notation here. So it says find each sum. So there's different parts of your sigma notation. So I'm going to go over the parts of it in the first example, and then I'm going to have you find the sum of all the rest of them. So in this first one, the bottom is what's called your lower limit. This is basically where you start. And then the top number above the sigma is your upper limit. Tells you where to stop. And this number outside the sigma, that is your rule, okay, or the formula that you're going to follow. So you would start off by substituting 1 in for I. This is not the imaginary unit I. Okay, this is just being used as a variable. So I would start off and I would say, all right, this is 3 times 1 plus 3 times 2 plus 3 times 3 plus 3 times 4, and then I'm going to stop when I get an I value of 5. So now you're going to go through and you're going to add all those up. So this is going to be 3 plus 6 plus 9 plus 12 plus 15. And when you add all those together, you come up with a sum of 45. So you're just finding, however many terms up to that upper limit between your lower limit and your upper limit, and then you just put that value into the rule, find out each term, and then add them all together. So what I want you to do now is I want you to go ahead and find the sum of each one of those for parts B and C. All right, so you should have gotten 90 for part B and then 2.718. So my question is if you were in part C, if you were to continue adding terms, what value would you, or what number would you start to approach? Good, some of you have been paying attention all year. All right, let's wrap this up with series. So at the bottom here we have for an infinite sequence, okay, so that means that there's no end to the sequence, it just continues on. The sum of the first n terms is also, it's called a finite series. So if I say, all right, I only want the first 10 terms, then now you're putting an end to it, so that would be finite. Or it's sometimes referred to a lot of times as the nth partial sum. So I might say find the 10th partial sum. You're looking for the sum of the first 10 numbers. So if you look at part B, it says the sum of all of the terms of an infinite sequence. So look at, as you notice, your upper limit there is infinity. Okay, so if I continue to add terms, sometimes it's going to approach a value, and so you'll actually get a number for the sum of an infinite sequence or series, and then sometimes you don't. It's because you're continuing to add more numbers. So there are certain cases when you have just a value for a sum of an infinite series, and then there's sometimes when you can't find a value. So for this next part here, it says find the series, and we're going to change this. I had a little typo. This should be 3 divided by 10 to the I. Okay, it says find the third partial sum. So if I want to find the third partial sum, I'm only finding the sum of the first 3 terms, which means I would put 1 in for I, 2 in for I, 3 in for I. So I'd end up getting 3/10 plus 3/100 plus 3/1000. Okay, and when I add those all together, I'm just going to get 0.333. Now, if I wanted for the entire series, what's going to happen is I'm just going to continue to add 3's on here, and it's going to look like 0.3 repeating. So if I wanted to find the sum of the entire series, it would just be 1/3. Okay, or it would be approaching 1/3. All right, so you guys have a Math Excel assignment. Okay, hopefully you got all the questions right as you were going through this video. If you have any questions, make sure you ask me in class. Until next time.